Hi, everyone, and thank you for joining us today at ProQuality Community. My name is Vyacheslav, and today we will be exploring the fascinating world of embedded systems. We will dive deeper into the fundamental principles of such system and explore how we can ensure that the quality of our that we can ensure the quality of the device that we use on our daily basis. This is the second event that we are organizing with our collaboration with Andersen IT community, and we are privileged to have here Luís from Portugal, our speaker and a TQB test manager, who is a certified professional with 8 years of experience in embedded testing. Louis has worked in such companies like Capgemini, FASEC, and Bosch. Louis, it's nice to see you here in ProQuality community.
Thank you. So,
yeah, embedded. I believe that embedded testing is such a complex subject. Could you please give our audience a bit of information what they can expect from today's session?
Yes, sure. So, hello everyone. Thank you for participating on the session. And today we will have and move in different topics, and we will start from definition and characteristics of embedded testing and systems. Then we will have a look on some architectural parts and main parts of these kind of systems, the process, how to create the embedded system, see the tools and technologies that normally are used to create and test embedded systems, test methods, importance of testing. We will have a look on a case study of one project with different technologies, how they are connected and how they are used in a real case project. We will talk a bit about ASPICE, then I will trigger information about future challenges, and in the end, conclusions and questions.
Thank you so much. So looks like this session will be quite interesting for our audience. And before we move to the main part of our session, I kindly ask you to post all your questions using our chats, and we will address them in the end of the session when we have a Q&A session with our speaker. So without further ado, let's get started. Louis, over to you.
Thank you for this introduction. And let's start our session. So at first, I would like to present to you the definition of embedded systems. So what it is, what it means, and in a practical way, how can we define it? So as definition, it's a combination of hardware and software designed for a specific function. So we have the hardware and the software, and this software will run inside of this hardware. And it should be ready and used for a specific function in a specific environment. So, but where are they? Where are the embedded systems? Where can we see where they are? So in our daily life, they are everywhere. We can see in gaming, so in consoles and other media devices, in intelligent houses where we have some kind of remote control for kitchen, for robots in our home, for automate some things that we have in our houses. So they are everywhere. In terms of automotive, we have it in a lot of parts of our car: infotainment, autonomous driving, powertrain. So they are also very focused in automotive industry. Also then, in medical devices, we have a lot of embedded systems implemented. Then we have more examples like communication, so our cell phones, for example, robots and production industry. In production lines, in factories, we have a lot of embedded systems to automate processes, to increase the production and develop better and more the products. And also in nautical and aviation industries. There are two parts where we also can see a lot of embedded systems, and they are being developed and growing. So after that, it's important to understand what are the characteristics of the embedded systems? Because they have some specification, let's say, or they follow more or less some group of characteristics. Of course, we cannot say that all of them follow all characteristics, but in general, they touch a bit each one of that. So let's start for the first one, dedicated. So as we saw in the definition, the embedded systems should be dedicated. They should have a purpose. They should have a functionality defined. A simple example, controlling a wash machine cycle, for example, or control an automotive braking system are two examples about a dedicated functionality for this embedded system. Then we have the real-time operation. What means this characteristic? In a big part of the applications, embedded systems are working and operating in critical applications. So operate in real time is critical because we need to react so fast to avoid issues with our embedded system and the behavior of that. For example, in automotive industry, we have the airbag. If we have an accident, the system should react quickly to launch the airbag and avoid accident and reduce the impact of that, for example. Then we have the resource constraints, what it means. So basically, in this kind of systems, we try to operate with minimal computing resources like CPU, power, memory, and storage. It will allow us to reach the next characteristic that is talking about low power consumption. Because, it's essential to have a good power management and have these devices with power management efficient to allow them operate better. Then we have the reliability and stability, because it must operate reliable over long periods of time. Of course, the failures should be at least predictable, and we have some kind of mechanisms to handle errors and recover the system when some fails occurs. For example, the turn off the energy or other events that are common to happens in this field. So then we have the small size and low weight. It means in some cases, the size and the weight are minimized to fit within host devices. We have host devices where our embedded system will be saved, and then we will use it, and it should be small and easy to be managed in this way. Another point is about interfaces and connectivity. So embedded systems are connected with other systems and connected with other parts. And because of that, the interfaces are crucial and a characteristic of these embedded systems. We have communications like I2C, SPI, UART, Wi-Fi, Bluetooth, Ethernet, IoT, and other ways to communicate between different parts. Then we have the security features. It's related with protection against unauthorized access and cyber attacks to our system. And in the end, other characteristic is about the interface, user interface, where these systems can interact with the user through buttons, LEDs, displays, and other HMIs that are implemented in this product. So then we have a look on the main architectural parts of this system, the embedded systems, and we will start for microcontroller. So the microcontroller is the brain of the embedded system. What it means, it's responsible for executing instructions and processes data. So like our brain in our body, this equipment receive informations, analyze and process them, and send informations to outside. More forward, we will see better how it works and how it's interacted in this system. But the main idea is that this is the brain, one of the main parts of the embedded system. Then we have the memory, another very important part. And here we have two types, ROM and RAM. ROM stores the firmware, that it's the software that it's running in our embedded system, and other non-volatile data, like flash or EEPROM. Then we have the RAM, where temporary data storage and stack operations during execution is saved. We have examples like SRAM and DRAM. And in that two pictures, we can see examples of these memories. So then we have another part like input-output interfaces, and it's used to communicate between embedded systems and external devices. In these pictures, we can see examples of pins that we have to receive these inputs and outputs, and they can be from two types: digital, when the proposal is manage digital signals, and analog, for analog signals. We have on the third picture, on the top, analog signal, and in the bottom, the digital signal. They are different, and in some cases, we have ADCs and DACs that are an analog digital converter, and the reverse, to convert signals from analog to digital and digital to analog. So then we have the sensors and the actuators. So another important part of our embedded systems, and basically the sensors are used to convert physical phenomena, example temperature, pressure, into electrical signals that the microcontroller can process. Basically, it's like sensors, like we have in our body to understand the behavior around us. We can see, can taste, we can hear, and we can understand the behavior around us. And these kind of sensors will send through electrical signals information to our microcontroller. Then the microcontroller will understand the behavior around us and then send electrical signals to actuators like output. And then it will act accordingly. Actuators convert electrical signals from the microcontroller into physical actions. For example, motors, LED, it can be a movement, it can be a light, or can be a sound. In this slide, we can see a practical example about that. We have here on the left side the inputs like cameras, motion sensors, temperature sensors, and sound sensors. In the middle, the microcontroller that it's normally assembly in some board. Here we have some examples like Arduino, STM32, Raspberry Pi, and in the end, the output, what our system will put to outside, can be through lights, sound, fans, or robotic arms or other movements or things like this. It's not mandatory to be like this, but can be other variances of these devices. So, and then we already know what are embedded systems, where they are, and what are the main parts, but how can I create embedded systems? So what is the process to create one embedded product? And then we have this workflow to explain it better. First phase is about requirement analysis, where we have to understand and document the specific needs and constraints of the system. In this phase, we involve stakeholders, customers, engineers, and regulatory people that allow to follow the regulatory rules. We define the requirements, and the output is requirements specification formally done. Then we move to the second phase, call it system design. In this case, we will be created a design of our old system, but based on the input from the previous phase, requirement specification. Basically, is create the system design following the requirement specification defined before. Here is defined the overall system architecture, select and design the hardware components, and create the software architecture. Specify also the communication protocols that will be involved and preliminary models and simple bases. And then the output will be the design specification. Then we will go to hardware software implementation. Here we will develop the hardware and software components of the system based on the design specification received from the previous phase. And here we have some activities related with the hardware where we create the schematic, electronic schematic. We design the PCB, choose the components to put on this PCB, and assemble all the parts. The same in terms of hardware, we write and test low-level programming and integrate the software models. And in the end, after join of all of that things, we will have a prototype as output. And this is the outcome of this phase. Then we have the testing phase. That's the fourth phase. And using this prototype, we will validate it. We will run some kind of testing like unit testing, system testing, regression testing, and other types. And the output will be a validated and verified system ready to be deployed for the market. Then in the deployment phase, we will deploy the system, and there are some activities in this phase. Install the hardware and software in the target environment, so in the real environment, configure the settings, and do the initial tests in the real environment. And in the end, we have maintenance to keep and to make sure that the system works and don't need any kind of fix and everything is going well, use it, and matching the client expectations. Then we will have a look on tools and technologies, because we look, okay, this is the process to create embedded systems, but what tools and technologies I need to create this? So here I would like to share with you some tools used in testing and also development. We can see in tools and frameworks like Cantata, Canoe, MATLAB and Simulink to manage data, Google Tests for testing, and others. Program languages, the most common, based on my experience, is C and C++ for low level in terms of embedded systems. But we also have C#, Python, Java, and Dart. But that languages are more related with high-level testing. But it depends for sure of the project. We also have the communication protocols, CAN, IoT, Bluetooth, I2C, SPI, and others. And about test documentation, we use Polarion, TestRail, Jira, Azure DevOps, and other test management tools to manage the testing artifacts. But then, okay, we are talking about embedded systems. We already know the tools, but here a question related with the testing. Why it's important to test? What is the motivation for that? Because we spend time, resources, and it needs to have a purpose. Yeah, our product is developed and the tests are important because we need to ensure the reliability and stability of the system to guarantee that the embedded system perform the functions consistently over the time. This is one of the motivations. Also, we have the standards compliance to make sure that our embedded system is according the standards of the market and the rules and regulamentations from that the market requests to us. Quality assurance to make sure that our product has quality and is a product that is certified and ready to be in the market. Performance optimization to make sure that our product is not only working, but working well with good performance and following the requirements defined. Security assurance, yeah, it's because of the cybersecurity and the hacker attacks. It's an important point, and it's a motivation also for testing. And competitive advantage. This is obvious when we have a product with high quality, well tested, following the regulamentations, our product will be in advance competing with other products in the same market. And now, we are testing the product, we already understand why it's important to test, our motivations, and why it's very important. And imagine that we fail in this phase of testing. Let's imagine that for some reason, some defect passing from different test levels, from different phases, and reach the market. I would like to present to you today one famous case of that. The case is Toyota's issue during 2009 and 2011 and affected some models like Camry, Prius, Lexus, and others. So what was the defect? Electronic accelerator control system failures due to software and electrical issues. So it was an issue in this system of the car, and no one was detected it until it be in the client side. We can see here on the pictures the example of the model of the car, here the part of that, Toyota, and in the last one is some journal news where they announce that this issue killed some persons in the world. So it was some fail in terms of testing, and the consequences were a lot. First part, money consequences, recalls and repairs, $2 billion. Legal settlements, $2.3 billion. So this is so bad for the company. Over than 100 accidents, some of them fatal. 9 million recalled vehicles globally. So a lot of people was recalled for this because of this issue. Yeah, and for the reputation of the company, it's also so bad. 9 million of people. And in the end, the stock price dropped 12%. So it's a big impact in the company, and for sure, it gives us the importance of testing and do products with high quality and following all the regulations. Then we will talk about test methods. So we already saw about the development, how create the system, importance of testing, practical cases, tools, but let's see how are the test methods? How are we testing the embedded systems? Here we have the V model, that it's a common approach followed in embedded projects currently. And we have on the left side requirement analysis, architecture design, and component design that are development activities. On the right side, we have testing activities, unit testing, integration testing, and system testing. As you can see with these icons, unit testing is like test a small piece, integration tests is test the connection and some pieces together, and the system test is the complete system. So let's start for unit testing. In unit testing, it's focused on testing components in isolation. The test basis is the detailed design, code, data model, or component specification. Objects, units, code and data structures, classes, and database modules. Here we have an example about that, where we have the source code, unit documentation, and the model diagram. 3 examples of our test basis. Here is the unit test created by that. To simplify, it's basically a function that calculates the speed with the distance and the time. If the time is less than 0, reports error. If distance less than 0, reports error and returns the distance if everything is okay. Here there are some test cases for that, unit testing. And here we have, as I said, the code, the unit documentation, where you can see here by text what are the inputs and outputs of the function. Here we can see the formula to calculate the speed. Yeah, and here another kind of information and approach about these kind of models. And basically, based on one of that or in all of them together, we create and derive our unit tests for this unit, this function, calculate speed. Then we have the up-level integration testing. So in this level, it's focused on testing the interfaces and interactions between components. The test basis is software and system design, sequence diagrams, interface and communication protocol specification, workflows, external interface definitions, and about test objects, we have subsystems, infrastructure, interfaces, APIs, and microservices. We have here example of an integration test. In the previous one about unit tests, we are talking about only speed model. In this case, we have 2 models. We have the speed and the GPS model. And we see that the model 1 calculates the speed, send it through this interface to GPS, and GPS can apply some functions. And this integration test was done here, where we calculate the speed, basically, we update the GPS speed. This is a function called in GPS model, and the first one is called in speed model. And then in the end, we will verify if the value displayed on GPS is the same sent by the speed model. Of course, it's a very, very basic test, but the goal here is understand the concept and understand the communication and connection between the models and how are you testing, how we are testing this type of integration tests. Then we have the system tests. As I said, it's the level that tests the full system, and it's focused on the overall behavior and capabilities of the entire system or product. So the test basis is system and software requirement specification, functional and no functional, use cases, epics and user stories, models of system behavior, state diagrams, system and user manuals, and the test objects, applications, hardware and software systems. And here we have example about that. Remember the previous test levels. First one, unit tests only about speed model. Second one, integration tests about speed model and GPS model. And now we have system tests. We have a lot of models connected, 3 dots here representing that we can have a lot of them more. And here, example, also simple, about the system tests. In this case, it's validating the speed model, GPS model, and infotainment that we have here. But we can verify different behaviors and different points of the system on this test level. Now we will talk a bit about no functional testing. So it's also an important part in terms of testing of our system. And we have then the performance. Basically, this point measures how the system responds under different load and stress conditions. Then the usability evaluates user to interaction with the system, ensuring a friendly and intuitive experience. Reliability tests the stability and reliability of the system, including its ability to handle failures and ensure continuous availability. Security, again related with unauthorized access, cyber attacks, and privacy of our system. Compatibility, make sure that the system is compatible with different devices, browsers, operating systems, and environments where it will be working. Efficiency, assess the efficient use of resources such as memory, CPU, and network. It's an important point about of the energy management. Maintainability evaluates how easy is maintain the system over the time, about including design the system by models to be more easy to maintain during the time and change and model or update it. So portability, it's about how easy is transfer the system and the product from different places and the platforms and without lost the functionality. About availability, it's to ensure that the system is available and accessible when needed and reduce the time and interruptions in that. And scalability, the possibility to increase the load and data volume, keeping the performance and the functionality. And that is some examples of tests, no functional tests that can be applied in our embedded system. So then we will talk a bit about automation, because it's a topic connected to the embedded systems, because is in a lot of projects it's a goal to automate the tests. And when we are talking about automation, the definition is use of software tools to execute predefined tests on a system automatically. There are some benefits, because it's possible to repeat tests under the same conditions easily. It's faster to run than manual testing. We will see in the next slide the pipeline and how possible is run it. Can run a big number of test cases. Evaluate easily the impact of software changes. Basically, we deliver something to our repository, and then we can see if it impacts the other models or components of the system. and reduce the human errors. But for sure, automation has risks. For example, the initial setup of environments and integration tools can be complex. Yeah, it can be complex to prepare the environment, to prepare the team, the project to start the automation. Then they have a significant initial investment in tools, infrastructure, and training. And automated tests can be less flexible and adaptable to rapid and unexpected changes. So the point on this slide is, okay, automation is a positive point, but it's always needed to understand and reflect under the risks and understand the good point and consider the team, the tools, the environment, the time, the costs, and the resources before move forward with automation. Here we can see 3 types of builds are examples based on my experience in different projects. We have nightly builds, basically are triggered automatically and run all test cases every night. We have a commit build, triggered automatically and run test cases related with components affected by the commit. Basically, I commit, imagine one source file related with some model, and this will run only the test cases related with this model. Don't run all the tests. And manual build, it's triggered manually and run all test cases immediately. The famous tool used for that is Jenkins. You can see the symbol here. And on the left side, you can see the appearance of these runs and these builds. Here we can see the comparison between automated tests and manual testing. So as we can see, according to the time, how much time better is moved to automated testing than manual testing in terms of time and number of test cases. Then we will have a look on automotive industry case study. Here it's a project from automotive embedded project, and where we have different tools, and we can see here tools and methods. For example, in terms of process, we use the V-model, Kanban, and Scrum. So this is the process that we use in this project. We keep traceability, where we have a detailed design in Doxygen, documentation for our unit tests, that it's connected with bidirectional traceability with Rhapsody, where we have the architecture, and then with Alm RQM and Cantata, where the unit tests were created. In parallel, we have Jenkins for automation and Splunk to present metrics. And for review, we have BVM review tool and AEEE for software version control. So the goal of this slide is present to you how can an embedded project be set up with different tools, how they are organized, how they are connected one to each others. And yeah, it's a generic overview about the embedded project where we have the different tools. This project is automotive project for a inertial sensor that it's used to measure accelerations focused to autonomous driving system. So now we will look a bit to ASPICE. So it's a standard that it's being implemented in a lot of projects and companies in the embedded world. And basically it's a standard for automotive, focus on that. The definition is the framework for assessing and improvement software development processes in automotive industry. So it's focused on the process. The objective is to improve the quality and efficiency of software development process in automotive sector. And application area, I already said, automotive industry and software suppliers for vehicles. And this standard is divided in some areas, in some parts. As we can see in this picture, we have supplier process group, acquisition process group, system engineering, and in the middle, software engineering process group. So here we can see a V model, as I presented before. And on the left side, we can see the development activities. On the right side, we can see the testing activities. So this is the way of V model divided in areas. And for each area, we have one part where we have the definitions and good practices to follow according to this standard. Then we will have a look on the maturity levels. So basically, ASPICE is divided in 6 levels, starting from 0 and finishing in 5. For each one, ASPICE says, imagine for level 0, the process is not implemented or doesn't achieve its purpose. And the maximum level, the process is continuously improved to align with organizational goals. So in the end of the ASPICE audit, one level of that is evaluated to the company and to the project, and the audit says, okay, you have certified as ASPICE level 2 or 1 according to the audit and the things that they found. Talking about in audits, I will present to you quickly how the audits are managed. So this is a process, okay? And it started with the preparation. So the first phase is defining the scope, the auditors, and schedule the audit to ensure the necessary documentation and personnel involved on this phase. Then we have the documentation review, where the auditors will have a look on the process and align with ASPICE requirements. Then we have the on-site assessment that it's conducted with visits, observations, interview, and verification. Then the process evaluation about the requirements and maturity levels regarding the findings and the work done together with the team and the previous phases. Next phase is compile audit findings and classify them based on severity and impact. So this document is shared with the stakeholders and it will be useful for fix. Then the follow-up and closure, we share the audit report with audit and discuss the findings and develop a corrections plan. We will implement a plan to improve and fix all the findings, and then we can call again for the audit. And in the end, we will continue improving the process and focus on the findings and the methodologies shared by the auditors. We will continue working on this way. So I would like to share with you also some examples of ASPICE, so what we have on this document and what kind of appearance it has. For example, we can see BP, that means best practice, and we have here some recommendations. For example, perform static verification of software units. It's one best practice for unit testing. So another example, for example, best practice 7, summarize and communicate results. Summarize the unit test results and static verification results and communicate them to all affected parties. So, and based on this kind of best practices from ASPICE, the auditors will ask our team, our project, okay, are you doing this? Show me how are you doing this? And we show to them, and in the end they say, okay, it's okay, it's not, you will have the level 1, 2, 3, it depends on the evaluation of the auditor. But it's something like this. We have the best practices, we have the project, and we need to show how are you following each best practice in the project. Then, embedded systems has a lot of future challenges because, as you know, the world is changing, new technologies are coming, and we have challenges that are coming also for embedded systems. For example, the increase of complexity. The modern embedded systems are becoming more complex and integrated with multiple functionalities. For example, in the cars, we have the infotainment, autonomous driving, connectivity, all of them in the same platform. So it increases a lot the complexity in terms of embedded systems. About automation, it's about automating the tests or the systems. It's also a challenge for that. In terms of security, it's related with the connected device with the Internet of Things and vulnerabilities from embedded systems against hacker attacks. Then the power efficiency is each time a challenge, more and more, because of the power management. Scalability and flexibility for embedded solutions to adapt in different cases and for future requirements and needs of the clients and the people. Another point is simulation and emulation of environments for testing. So it's also a challenge for embedded systems. Integration with emerging technologies. In this way, we are talking about EA, machine learning, 5G, are new technologies that will be integrated with embedded systems for the future, and for sure it will be a challenge. And of course, the electrical vehicles, that it's a reality that we are starting working on, and also a challenge on this field. So, and now I would like to share with you some conclusions, main overview about the presentation and embedded systems. Basically, it's about the critical importance of that. So, not only about embedded systems, but also from testing. It's really important. And when you're talking about critical safety environment, it's really important to do everything with high quality. Unique challenges here, it's related about the resource constraints, complex integrity, requirements, new technologies. So we have unique challenges when we are working in embedded systems and testing. The effective approaches, basically here about how we approach to create automation, to test, to design, to automate, and we need to have a good, efficient, and specific approach to pass and reach all challenges that we have in embedded world. Test benefits, based on the example that I shared with you about Toyota, I guess you already understand that test is a benefit for our system, and it's really important that we have certified products with high quality, with minimum errors and bugs possible. Then, to work in embedded, it's needed to have a multidisciplinary knowledge from hardware, communication, programming, electricity. There is a multidisciplinary knowledge that it's needed. Sometimes with different teams, different persons can join the knowledge to reach the goals. And in the end, real-world impact. Embedded devices are everywhere. Embedded devices are part of our world, and we need to live with them in this reality, actually. And now I can say that we can open the QA part of the session.
Luis, thank you so much for the interesting talk. I personally liked very much examples that you provided and the information. So before we move to the Q&A session, dear audience, I kindly ask you to scan the QR code that you can see on the screen. Following this link, you can rate our event and say thank you to Louis and give a badge to him if you liked our talk. So let's move to the Q&A session based on our chat. I see that the topic is quite interesting and I would say hot. So we have got a bunch of questions. So let's start. So the first question is the software development lifecycle waterfall for embedded systems? So,
okay. So thank you for your question. So based on my experience and the big number of projects where I work with, normally is mixed between vModel and Scrum. Scrum is more used, I guess. But in some specific projects, waterfall is also used. So it's hard to say that we have a rule for this definition for embedded system software development lifecycle, because it depends on the project, how big is the project, the resources. There are some variants, but the answer is yes, it's possible to have this process in waterfall and in Scrum, depending on the project.
Okay, so agile is possible even in embedded systems, but based on some conditions, let's say.
Yeah.
Okay, cool, very good. The next question is, with which cloud do you have more integrations?
Okay, with which cloud we have more integrations? So here we are working more with clouds. So I'm not understanding well the question, but I guess it's related with IoT.
Provider, probably not. But
Yeah.
yeah, but I'm not sure. Which cloud provider, maybe, or maybe something else, I don't know.
Yeah, but I guess it's connected with IoT. So in embedded testing, embedded systems, we are using the cloud to do the updates of the system and the firmware. So basically, it's loaded by IoT, and it comes from the cloud, and it's stored that.
Okay. Okay, cool. Let's move to the next question. Thank you. This question is from Dmitry. Hi, thank you for the great introduction. When testing embedded systems, should the tester visit the client's facilities, or can the testing can be done by tester in their own location?
Yeah, it's a good question. Thank you. So it depends, but for sure, I suggest always to have some time together on site of the client. At least on the ramp-up phase, it's important to do it quickly and to do it well. Of course, there are projects that we have the devices and the hardware in the tester side. So the client is so far, and we have the benches and the boards in our side. For example, in Andersen, we have a laboratory for these kind of things where we have different test benches, and they are tested in our side. In other projects, the equipment is on client side, and we access them remotely. In both approaches, my recommendations and what I always prefer is to have at least the ramp-up phase with the client to make sure the configurations and the system setup is done well, quickly, and with a good understanding.
Cool. Thank you. Thank you for your answer. Let's proceed with the next question. Which programming language is better for embedded system testing? It has been covered, yeah. But let's sum up.
In this case, for example, if we are talking about low-level testing, for example, unit tests, I would say C, C++, Python, more low-level languages. When we are talking about integration and system tests, I would say Dart, C#, also C++ can be used here. But this is more or less the distribution. There isn't a specific program language excellent for embedded system. But if the question is, I would like to start a career in embedded system, what language should I start? My suggestion is C, because the relation between difficult and learning is good, and it's a base language for C++, and then it's more easy to understand other topics. Of course, it depends on the people and the goals, but at least it was my experience, and I'm sharing this.
So, guys, take into account if you want to start with embedded systems programming. Okay, let's move to the next. In the context of embedded systems, what are the most effective testing strategies, particularly in safety critical applications?
Yeah, it's a good question. So here we have a combination of two parts. So we have testing techniques that are defined by STQB, for example, black box, state machine, checklist, experience base, or whatever. And then we have some kind of standards that help us to reach these levels. For example, ISO 26262. Basically, this standard say us also good practices and how to follow in order to work in critical safety environments. They have ASILs that are kinds of critical parts, and it was a part of our presentation, but because of the time frame, I didn't talk about that. But it's a standard like ASPICE. Basically, it's the ISO 26262 that allow us to manage on this way.
Okay. Thank you. Thank you for the answer. The next question is there some extended legal financial liability in case of testing safety critical systems?
So yes, in terms of that, we need to take care about that. As I show you in the presentation, the consequences of that are so high. So we need to make sure and take care about this and work with high quality, because the legal and financial consequences of issues can be so big.
Thank you. So, guys, again, take into account this information as well. The next question: what approach can be used to test components functions which directly work with the memory of target device?
Okay, so let me understand the question. What approach can be used?
Probably when there is no much space, maybe on the device. No. So which approach to use? No.
Yeah.
Something
So here we have some tools that allow us to test about the memory, and also in some cases we need to test and check memory leaks and work and test in terms of performance if the system, how the system works when the memory is being reduced. So we have different tools and methodologies that can be used for that. We can increase the memory and reduce the memory space and see how the behavior of the system be. How quick is the response, how other applications are running. Yeah, this is, for example, one approach for that.
Thank you. So the next question, I think that actually most of approach probably can be reused here in embedded systems, like we use, for example, for other, I don't know, systems. The next question from Dmitry: what are the key requirements and qualifications for someone planning a career in embedded testing?
Okay, good question. So normally, of course, it's not a rule, but the big part of the positions request for electrical engineer, informatic, or mechanical, or something similar. It depends on the way. For example, for manual testing in embedded, you don't need to be expert in some programming languages. You can run the tests manually, and that's okay. In other ways, the programming languages are very important. And as I told you in the past, I guess C language is the best to start based on my experience and in the work that I did. And of course, it's important to have also some kind of knowledge about communication protocols, electricity, hardware. Yeah, mainly on that part. So you can also start from simple things with, for example, Arduino initial kit, that it's one board that it's very simple to program and also can be programmed with C. Yeah, so, and that are the basis for that.
So guys, if you want to start career in embedded testing, some special technical background is highly recommended here, including programming language, low programming language, right? Okay. So the next question we have is, could you describe the most interesting complex system you have ever tested?
Yes, for sure. So the most interesting is different for me, the most complex, at least in my case. So the most interesting was the most interesting is the inertial sensor, because it's interesting because I saw this sensor working, and it seems very simple because look, it's a sensor that measures speed. Okay, it's very simple, but it was interesting because inside we have some kind of factory, because we have the sensor that receives some kind of signals, and we have 16 places where we do operations with these signals. So the complexity inside is high, but it was interesting for that, because a small sensor with a small functionality has a lot of complexity inside, like relation of signals, maths, a lot of things, removing of noise. Yeah, it was the most interesting. The most complex, to be honest, was in the kitchen industry, when I tested the product that wants to control the kitchen with the cell phone through Bluetooth, turn on the cooktop, turn off, do things like this, cooking autonomously. And it's very complex because the Bluetooth feature has a lot of issues, and it was very hard to test because it failing sometime, but in the end we reached the goals and everything worked fine.
Are you using such system in your own home?
Oh no, I
Okay.
guess this system is not yet on the market. It's a prototype.
Okay. That's interesting. Thank you for sharing.
Thank you.
Cool. Uh, Next question, probably one of the last, as we are running out of time. What skills should an embedded tester should have, and how much time it will take for transition? So I think that we have covered it, but if you want to add some details.
Yeah. In terms of technically, so it's already covered. In terms of soft skills, it's similar to other testers. So basically, attention for the detail, focus in high quality. Yeah, mainly that parts and covered for the other answers that I give. About the time of the transition, it's hard to say, but I guess it's important to divide it in two phases. So the first one is study standalone, do some courses, do this C programming, have fun a bit with Arduino. But in some level, it's important to join the project because in the real case, in the real project, is where you will have this experience and increase your expertise on this field.
Cool, thank you. And we have the last question for today. Tests in parallels. Do you have such practice? And you use already created systems to emulate device or write your own?
Yeah, so normally, at least in the projects where I work, it's done. So basically, we have our product, for example, our board, and then we emulate the completely system around. For example, imagine the car that we are testing infotainment of the car. We will not have the car in the office or in the client side. We have only the infotainment, and we emulate everything around. The same in the kitchen. We have the small board and the small devices, all free in PCBs, but the environment around is emulated. So it's a common practice, emulate the devices around of the embedded system, at least in the development and testing phase.
Okay, thank you so much. So looks like we have all questions answered. Luis, thank you so much for joining us today at ProQuality community and sharing your own knowledge about embedded tests, embedded systems, how to test them. We will add all materials related to this session into our talk page along with the recording, and we will send a feedback form within an hour. So guys, please help us to improve our events in the future. I think that's all for today. Stay tuned, join ProQuality community in social networks, and may your test always be flawless. Lee, thank you so much one more time for joining us.
Thank you for all, and thank you all for participate and join this event. It was a pleasure.
Have a good the rest of the day to all.
Thank you.
Bye-bye, guys.
For you too. Bye.